Hi everyone. So in this section we're going to be talking about separating working and long-term memory. And so we've already talked a bit about working memory and what it is. We've come up with an introduction for what long-term memory is. And I want to talk about the way that these two kind of memories are separate from each other. But before we do that, I want to just kind of provide a brief overview of long-term memory and compare it to what we already know with working memory. So one of the big things that differs between working and long-term memory, as the name suggests, is the amount of time that that information's held. And so while working memory, we can think of it as kind of RAM in a computer, or if we look at it historically, the amount of space in a loading dock. But right, it's a very small form of memory where things are very, very fragile and only stay in working memory for a short amount of time. In fact, you need to rehearse in order for that to stay in working memory for a period of time. Now, long-term memory is very, very different. In a lot of ways, you can kind of think of it as like a library for memories. And that's why I have here that long-term memory is like an archive, right? It's like a library where we have these memories stored in the brain, and what we can do is go and retrieve them, much like we would retrieve a library book. Now, when we talk about the time span of working memory, the time span is very, very short, right? Just fractions of seconds while we're actually working on it. In the case of long-term memory can cover anything from a period of seconds up to infinity, right? I mean, there are some memories that we've had for a really, really long time. If you think back to when you were a child, there are some of your first memories or early memories that are still there, that you still remember either that event or the information that you learned there. So the time span of long-term memory covers from seconds to infinity. Now, even though there's kind of this infinite store, right, one of the things to kind of keep in mind too, though, is that the details of those memories drastically differ. So even looking at the same time span, so thinking back to some of your first memories, some of those might be very rich and vivid memories of something that's happened to you, and others you kind of remember, but the details are a lot more fuzzy or a lot less clear. And so that's another issue that we're going to address as we start talking a little bit more about long-term memory. And to kind of highlight that long-term memory is an archive too, the capacity for long-term memory is very, very large, right? Just like a library, it's very large. There's a lot of information. Now, this contrasts greatly with working memory, where the capacity is relatively small, right? 7 plus or minus 2. And so long-term memory has a very big, big capacity. Now, one of the biggest ways, or one of the ways at least, that we'll talk about measuring long-term memory is something called a free recall task. And so what happens in the free recall task is that the participant hears about 30 words. And basically these words are read to them, and then what they need to do is they're told to recall the word list, and they recall as many of the words as they possibly can. And so we're actually going to try that here. So I have a free recall task example for you. And that's basically what I'm going to do, is read a set of words for you and ask you to recall as many as possible. So we'll go ahead and transfer into that example so you can get some experience with it. Okay, so we're going to try a free recall task. And like before, basically what's going to happen is I'm going to list approximately 30 words. And what I want you to do is to remember these words. And then after I'm done repeating the words, what I'm going to do is say recall. And I just want you to recall as many of the words as you can for me. Now, you may want to write these down just because we'll come back and talk to them a little bit. So definitely feel free to have a piece of scratch paper and write down all the words you recall. But we'll go ahead and get started, and I will start saying the words that I'm going to ask you to recall in a minute. Power, general, 10, confrontational, little, disconnect, decoder, revenge, distant, fearless, clever, muzzle, thick, plaid, flatten, retreat, shackle, commercial, rib, basket, excuse, badger, contestant, elongation, cola. Okay, and recall for me as many of those words as you possibly can. Okay, so how did everything go with the free recall task that we tried? Now, I had to do this task for a couple different reasons. One, we're going to talk a little bit about how this task kind of demonstrates the role of and separates the roles of working and long-term memory. But then the other reason that I had you do this task wasn't just to see how good you were at the task, but to really demonstrate kind of a general finding that comes from using this task. And that particular general finding is reflected right here in this graph on the right hand of the screen. So for this particular task, we find that the words that people remember are very specific, or usually tend to be very specific. And so here we have the percent likelihood of recall, and we have something called the serial position on the x-axis. Serial position just refers to, so the serial position of 1 is just the first word in the list, the serial position of 5 is the fifth word in the list, and so on and so forth. Now, one of the major findings of the free recall task is this thing called a serial position curve. And the serial position curve, basically what we're seeing here, is that the words that people remember in the list tend to be at the very early beginnings of the list and at the very end of the list. And so this early part of the list where you see that people remember a large number of words from the beginning of the list is something called the primacy effect. This benefit of remembering words, almost remembering at least the last several words that they heard at the end of the list, is known as the recency effect. Now, for this task, people typically remember about 12 to 15 of the 30 words that they're presented. And those 30 words are given to specifically make the task hard so that people aren't going to remember all the words, that there is some forgetting. In the case of the primacy effect, basically what ends up happening is that you remember the first few words because you're committing those words to long-term memory. Now, chances are good that when I was giving you the list, one of the things that you did to kind of deal with this list, especially knowing that I was going to ask you to recall the words off of it, is you rehearse the words back to yourself. So you were, as I was presenting the words, word one, word one, word one, and then word one and two, word one and two, word one and two, and you just kept on doing this. And eventually there was some point where you just weren't able to continue rehearsing in between the time that I was giving each of the words, and that eventually broke down. Now, by the process of doing that, we'll talk about this more in a minute, but in the process of doing that, basically what you were doing where you were committing those first few words of the word list to long-term memory through the process of rehearsing it over and over again. Now, in the case of recency, basically what that's reflecting is the words that were stored in your working memory. So the reason that you remember those words at the end of the list is because those are the words that are currently in working memory when you're asked to recall that task. So let's talk a little bit more about this particular pattern. As I've already said, the recency effect really reflects what's in a working memory. And so as new words come in, the words are in working memory. As new words come in, those old words get bumped out and replaced with the new words, right? And so most people remember the end of the list because there are no additional words to bump them out of working memory. Similarly with primacy, like I was saying before, you had a chance to mentally rehearse. Through that process of mental rehearsal, you were basically storing those words into your long-term memory. And granted, those words aren't going to stick in your long-term memory to infinity, but these are in your long-term memory. So that's what causes the serial position curve and also explains the primacy effect, or the better remembering of words at the beginning of the list, and the recency effect, the better remembering of words at the end of the list. Now, one of the ways that we can really kind of demonstrate that this is a working memory and a long-term memory phenomenon is that we can mess around with the task a little bit to demonstrate exactly what is working memory versus what is long-term memory. And so usually when this class is face-to-face, what I have students do is try to generate ways that we may basically mess with working memory. So is there something that we can do either during or after the free recall task that we can basically mess with working memory and presumably bump those words that are in working memory out? And it ends up that there is a pretty simple way to do that. As we've already talked about when we've been talking about working memory, one of the good ways to deal with working memory is to do some sort of math, right? And so, for example, one of the things that we could do is present participants with a word list, much like I did for you, and then just have them sit there for a small chunk of time, maybe 30 seconds before they start recalling the words that I presented them with. And that's something that's called a unfilled delay, right? We just basically delay things for 30 seconds. They don't do anything in those 30 seconds. They just sit there, and then we have them recall as many words as possible. Alternatively, what we could do is something called a filled delay. And so basically this says, okay, there's a time delay, and we're going to fill that time delay with some sort of task. Because of what we're interested in this particular case, it's going to be a working memory task. So for example, we could have them do something like counting backwards from 507 by sevens, right? Because this is going to require working memory in order to remember what our total is, and then subtracting 7 from that total, generating a new total, keeping that total in working memory, while we also count backwards by 7 to the next total, and so on and so forth. Now, in this particular case, basically what we find, and what is further evidence that this is a recency effect, and there's a typo in this particular slide, I apologize. Or actually, I guess there isn't, but we'll get to that in a second. But basically, here's the graph that we were looking at before, right? And this is the serial position curve. Now, there are 3 different conditions in here. The red line here just demonstrates what would happen if we did the task like I had you do it, where there was immediate recall. As soon as I was done counting off the words, you would recall the list back to me as soon as possible. And here we see our old friend, the serial position curve. We also talked a little bit about an unfilled delay, right? Where people just hear the word list, sit quietly for 30 seconds, and then they're asked to recall as many words as possible. Now, one of the things that you notice here is that they basically do the same as immediate recall, especially for the end of the list, which is what we're looking at with the recency effect. Now, the blue line here, what that represents is it represents the 30-second fill delay, where they were doing some sort of a working memory task. Now, what you'll notice is, especially for the end of the list, we see a different pattern in the graph. Basically, we see that people really tend to forget some of the last words that they were presented with. And so there's, right, a performance decrement where they do a lot worse on the task. And so what this shows is, just by using a filled and an unfilled delay, is that if we tax working memory in some way, such as having people count backwards from 507, then we're going to see worse performance. Now, where I got kind of screwed up as I was looking at the slide closer is that I want to highlight the point that we'll notice that it doesn't really matter what, if we use the 30-second fill delay, it doesn't really affect the primacy part of the curve, right? People still remember those words, and that makes sense because it's already in long-term memory. Our working memory task isn't going to interfere with the words that are already in long-term memory. And so what we see here is that the primacy isn't affected by this, which is suggestive of it being a long-term memory phenomenon. But when we mess with working memory, it does actually affect and have a negative effect on the recency part of the curve. Now, another way that we could kind of mess with the serial position curve is by dealing with the primacy effect. And so one of the ways that we could kind of mess with this is that we could just slow our presentation down. So I didn't time it, but I tried to present roughly about 1 word per second when I was giving you the word list. So one of the things that we could do is we could slow that down even more. So let's say that we slow it down to I present a word once every 3 seconds. Now, we already know that kind of the initial reaction when people are presented with this task is that they try to rehearse as many words as possible. If we slow down that word presentation, then that gives them more time to mentally rehearse, right? It at least is going to put it in different terms, it's going to delay that point where they're like, oh, I can't do the rehearsal thing, because the words aren't presented as fast. So as we slow down the presentation of words, it really gives them more of a chance to mentally rehearse. So let's see what happens when we do this. And so here, slow presentation, which is represented in the purple line. Let's just say that that's a presentation of the words at once every 2 seconds, where fast presentation is more like what I did when we initially did this, where the words were presented once per second. Now, One of the things that you'll notice is that in that particular case, when we presented it slow, much like we were suspecting, if this is really allowing people more time to mentally rehearse and to better store those words in long-term memory, that they're going to have better performance. And here, the fact that they're higher up on the serial position curve suggests that actually was the case, that they actually performed better when they had more time to mentally rehearse between words than when we did it kind of the traditional way that I did it for you, where they were presented the words at once per second. You also notice that this primacy effect lasts a lot longer, or I guess I should say at least a little bit longer, in the case of slow presentation too, right? Because with that extra time, people are better able to rehearse. Now, the other thing I want to point out here, though, is that when we look at the end of the line, when we look at the recency, that slow presentation doesn't have any effect whatsoever. In fact, these two particular lines are overlapping each other on this last word. So what this suggests is that the slow presentation helps with at least the primacy effect, but it has no effect on the recency effect. So suggesting that it doesn't have any effect on working memory, which makes sense. So just to kind of rehash what it is that we talked about in those particular two cases, we can really kind of show just behaviorally by messing either with working memory or long-term memory, is that we can show that these are two different types of memory that are involved in the free recall task. For things that are at the beginning of the list, it's a long-term memory phenomenon. For things that are at the end of the list, it's a working memory phenomenon. So hopefully that makes sense and shows why we can divide those two things and separate them from each other. Now, this evidence for this isn't just behavioral. There's actually a fair amount of neuroimaging evidence to suggest that when people do tasks like the free recall task, that actually different areas of the brain are activated. And so there's a fair amount of fMRI work that shows that hippocampal regions, which are associated with long-term memory, tend to be more active or activated when they're recalling words from the list. Specifically, though, it tends to be more activated when they're recalling words early on in the list, which again supports the idea that that primacy effect is really a long-term memory phenomenon. Similarly, for working memory, the data isn't as clear, but you do see more prefrontal activation when people are recalling words at the end of the list too. So, fair amount of evidence, both behavioral and neuroimaging, that suggests, at least in the free recall task, we're relying on two different types of memory, and we can separate those two different types of memory from each other. Okay, so one of the questions that comes up and that we should discuss is how information is coded in both working memory and long-term memory. And so we've already talked a little bit about how information is coded in working memory when we were talking about Baddeley and his component system for working memory, right? So spatial information, or spatial and visual information, were coded in one component as either physical spatial position in the world, or as some sort of a visual image that the brain used to kind of represent what it was that we were trying to remember. And then we also talked about the auditory loop, where auditory information was basically like a recording of listening to somebody's voice. And so whenever we talk about coding, basically what we're talking about is how stimuli in the outside world is actually represented in the brain. And so we've talked about this for working memory, and not surprisingly, information in long-term memory is coded in much of the same way. So in working memory, we talked about keeping a pattern, and in the case of visual coding in long-term memory, a lot of it's kind of physical representation of that. So for example, if you're thinking of a friend's face, then usually what ends up popping up is that there's some sort of a visual code for that friend's face. It's almost like a picture of that friend pops up in memory. And so that's what, in similar ways to working memory, that's how visual information is coded in long-term memory. Also similar to working memory, there's auditory coding, right? So if you think back to one of your favorite songs, it's almost like you can hear that song replaying in your brain. So, right, auditory information is coded in much the same way as working memory. Now, the other type of coding to talk about is something called semantic coding. And so, for example, there's the infamous year 1942. That's the year that the Columbus sailed the ocean blue. And in a lot of ways, when it comes to long-term memory, The semantic coding is how long-term memory codes such information. So you may not necessarily remember the specific details, but a lot of times there's some sort of a semantic code for the gist of what somebody's saying. So it's not like you remember me specifically giving lectures on the first day of class or anything like that you can go back and basically listen to that lecture again in your memory. But you get the gist of what I was saying. What are the basic course policies for this course? What is it when we talk about academic dishonesty, right? And you have a gist of that. And in a lot of ways, that's how semantic information is coded in long-term memory. So a lot of similarities between coding and working memory and long-term memory. So that wraps up our section on separating working and long-term memory. Hopefully that makes sense. If you have any questions, definitely let me know, either via email or the parking lot forum, and I'm happy to answer them.